All right, let's get started. So today we are still going to talk about isolation and concurrency control, and we are going to see a specific algorithm in order to do concurrency control. That algorithm is called two-phase locking. We are still discussing about the transaction manager in the database system, and the relevant chapter for what we discuss here, that is chapter 19 in the Ramakrishnan and Gerke book. So generally, we're currently discussing about concurrency control. And as a little reminder, concurrency control essentially takes as input a set of transactions which want to execute read and write operations on the database. The output of concurrency control, that is a schedule which orders the steps, the read and write operations from different transactions. And it may do so in a way such that it interleaves the steps from different transactions. So we do not execute one transaction after the other one, but we might execute a few steps from transaction number one, then a step from transaction number two, and then again some steps from transaction number one. But if we do this, we have to be very careful, because otherwise we create strange effects for the user and inconsistent data. And concurrency control is about making sure that this does not happen. So we want to find algorithms that can actually do concurrency control, and we're going to discuss about one of the most popular ones today. So far, we have been mostly discussing about what properties we want in one of those schedules. In particular, we have seen that conflict serializability is kind of a good compromise, because if your schedule is conflict serializable, it means that those strange effects due to interleaving multiple transactions, they cannot occur. So to the users, it looks as if everything executes serially, one transaction after the other one. On the other side, conflict serializability has the nice property that we can quite efficiently verify for a given schedule whether it is conflict serializable. And efficiency is very important, since concurrency control happens at runtime. So we do not want concurrency control to become the bottleneck. So we want conflict serializable schedules. We also want recoverable schedules. And as we have seen last time, that means essentially that one transaction does not commit until all the other transactions that it has read values from have committed before. Because otherwise you might end up with a database in an inconsistent state from which it is impossible to recover. So we want recoverable schedules. And we have seen a couple of other properties, avoiding cascading aborts and strict schedules. And depending on the scenarios, we might also want some of those properties. Now in the following, we're going to discuss about protocols, about algorithms that allow us to enforce schedules with those desired properties. And generally, ideally, we want mechanisms that allow as many schedules as possible that have those properties that we're interested in. Because if we can consider more candidate schedules, then we have better chances of finding one that is particularly efficient to execute. And therefore, we want to be able to consider as many schedules as possible. Now, a very popular variant of concurrency control is based on locks. A lock generally means the permission to operate on a specific object in your database. And before a transaction can do anything with a database object, which could, for instance, be one row in one specific table. Before a transaction can do anything with it, be it a read operation or write operation, it first must acquire a lock. So in order to acquire a lock, a transaction submits a lock request for the specific object to the lock manager, which is a component that generally administers the different locks and keeps track of which transaction has acquired which lock. Now, if a transaction requests a lock, that lock might not be immediately available, because maybe currently another transaction has the lock on the corresponding object, and we have to wait until the other transactions gives back the lock to the lock manager, and then the lock manager can distribute that lock again to the waiting transaction. So a transaction might have to wait a little bit until it obtains the lock. Once it has the lock, then it can start working on the object. Now, this is the high-level outline of locking-based concurrency control, but there is many variants, and in the following, we're going to see a couple of them. Let's start with something very, very simple. Let's say that we just make one big lock for the entire database. So if a transaction wants to do anything with the database, it first has to request the lock on that database, and it waits until it gets it. Then it performs its operations, and at the end, the transaction gives back the lock on the database to the lock manager. So that means that essentially only one transaction can hold this lock on the database at the same time. Does anyone have a quick comment about how you expect this scheme to perform? In the chat? Yes, very good. Okay, very good. I see multiple comments and all of them are correct. So yes, indeed, if we make one big lock for the entire database, then we're often unnecessarily blocking transactions from proceeding because different transactions might be able to work on different parts of the database at the same time. And if I really only have one big lock for the entire database, what happens means essentially only one transaction can execute at the same time. It acquires the lock at the beginning, it gives it back at the end. So that means what I'm essentially doing is that I'm executing transactions serially, one transaction after the other one. And the whole point of concurrency control and preparing transaction schedules was that we want to get better performance than when executing transactions serially. So this is probably not what we want. Let's refine it. Now, a first refinement uses the observation that there's many objects in a database, and what are the chances that two transactions want to access exactly the same object? So we should refine our locks to refer not to the entire database as a whole, but rather to specific objects in the database. So those objects could have different granularities. It depends on the implementation. For instance, we could say that one row in a table is an object. And if we have that, then transactions, they first of all decide which objects they are interested in. Then they request the locks for all those objects and wait until they get them. Then it executes. And finally, the transactions gives back all the locks at the end of execution. All right? So this already works better than before, because now different transactions can proceed in parallel on multiple parts of your database. Now, another refinement is the following. So we have seen when discussing about conflict serializability that conflicting operations, they always involve at least one write operation on the same object. On the other side, as long as I only have read operations, I could actually allow many transactions to proceed in parallel. The problematic operation is really the write operation. And in order to increase the number of transactions that can execute at the same time, I could start to distinguish between read locks and write locks. So a read lock, those are also called shared locks, allows you to only read the values of an object, but not to change them. A write lock, also called an exclusive lock, allows a transaction to read and to write the corresponding object. And if I have those different lock types, I can exploit them, because as long as transactions only want read locks, I can grant multiple locks on the same object to different transactions. All right, and now all of the transactions essentially have to decide whether they want to read an object only or whether they want to read and possibly write an object. Then they have to request the corresponding lock type for the corresponding object. All right, and again, the effect of that is that we can possibly allow more transactions to execute in parallel on our database. All right, now so far we have assumed that transactions request and wait for all the locks at the beginning of execution, and then they hold those locks until the very end of the execution. So at the beginning of execution, a transaction requests all the locks. At the end of execution, the transaction gives back all the locks. Now, sometimes it might not be necessary to hold an object, to hold a lock on an object until the very end of execution. If a transaction is done working on an object, it seems reasonable that a transaction already gives back the lock on that object so that another transaction can start working on that object before the first transaction is finished. Now, this refinement can be a good idea, but it doesn't have to be. It can be a good idea because it might again allow more transactions to proceed in parallel. On the other side, if you allow this, then you might have cascading aborts. And as a little reminder, what is a cascading abort? So if a transaction aborts, it generally means that all direct and indirect effects of this transaction should completely vanish from the database. So it should look as if the transaction had never happened. And if a transaction writes a value to an object and that value is read by a different transaction, the value could have influenced what the different transaction is doing. That means if the first transaction aborts, it has indirectly influenced the behavior of another transaction. So if you abort the first transaction, you also have to implicitly abort the other transaction that has been influenced by it. That is a cascading abort. And if you allow transactions to hand back locks before they finish executing, before they have to decide whether they commit or whether they abort, then what you see in this example here can happen. So here we have a write operation by transaction 1 on object A. And now let's say transaction 1 is done with object A, so it could already hand back the lock on A, right? So the lock manager accepts the lock from transaction 1 again, and then it immediately hands it out to transaction number 2, which is requesting the lock on A because it wants to read the value of that object. So this is what you see here. Basically, the lock changes hands from transaction 1 to transaction 2. And now, unfortunately, transaction number 1 decides to abort. And in that case, we would also implicitly have to abort transaction number 2 because something that this transaction did could have been influenced by the value that it read from A, and that value has been written by the aborted transaction. So if we allow transactions to hand back locks early, it means that we must accept cascading aborts, and then it becomes a design decision. There's a performance trade-off here, and depending on the scenario, one possibility might work better or the other. Now you might already guess the next refinement. So here we have relaxed the requirement that transactions hold their locks until the very end of execution. And now the next refinement is that we allow transactions to acquire locks not at the very beginning of execution, but sometime during their execution. Quickly checking the chat here. All right, and here there's a question about the last example. I'm quickly going to answer that before continuing. So here the question is, if R2 had read a different object, whether it could have been influenced by A or not. It could not have been influenced by A. So we assume that the database system knows all the values in the database that transactions read or write. So if the database system doesn't know about any read operation on A, then the transaction hasn't read the value of A and cannot have been influenced by it. And at least in the short example, it seems that transaction 1 is only writing to object A. So unless transaction 2 is reading the value of A, it cannot be influenced by transaction number 1. So Here we only talk about influence because one transaction reads a value written by another transaction. So in this case, if transaction 2 had read a different object than A, we wouldn't have a cascading abort. Great question. Let me quickly move the chat to the side. All right. Okay. Here we have refined and allowed transactions to release locks early. Now we're going to allow them to acquire locks late. So essentially, we have so far required a transaction get all the read and write locks before transaction processing starts. But strictly speaking, that's not always necessary. Because maybe a transaction wants to start working with object A, and it can already do this as soon as it has the lock on object A. Afterwards, it will continue working with object B. So it can delay acquiring the lock for object B until it is done with object A. And as always, if we reduce the time that locks are held by a transaction, it allows more transactions to proceed in parallel. That's always the advantage. One drawback about acquiring locks late is what you see in this example here. It's called a deadlock. You might already have heard about it. And it essentially means that transactions are mutually waiting for each other and nobody can make progress. So here, for instance, a simple example of 2 transactions. In general, a deadlock might involve more than 2 transactions, but in this example, it's only 2. And here, transaction number 1 acquires a lock on A, and at the same time, transaction 2 acquires a lock on B. Now, transaction 1 has the lock on A, transaction 2 has the lock on B. Now, transaction 1 wants to do something with object B, so it is now requesting the lock for object B. This lock is currently held by transaction 2. At the same time, transaction 2 is requesting the lock for object A, which is currently held by transaction number 1. So those 2 transactions each have one lock that the other one needs to make progress. And that means that none of them can make progress because they will wait indefinitely. Now, what happens in reality is that the database system detects the situation and resolves the deadlock by aborting one of the participating transactions, so at least the other ones can make progress. We're going to discuss much more about deadlock handling in the following lecture. But just so you know, there's again a performance trade-off here. If we allow transactions to acquire locks late, we might increase the number of transactions that can proceed in parallel. On the other side, we might have deadlocks, and that can have a bad impact on performance. So depending on the scenario, this is either a good idea or not a good idea for performance. Now, the title of this lecture is two-phase locking, which is one very popular locking protocol, which essentially combines all of the advantages that we have seen so far. Namely, first of all, it allows for fine-grained locks. We don't have one big lock for the entire database, but specific locks for database objects. It distinguishes different lock types: shared, meaning read locks, and exclusive, meaning write locks. Depending on the variant of two-phase locking, it might allow transactions to acquire locks late. Also, depending on the variant, it might allow transactions to release locks early. There is, however, some restrictions in general about when transactions might acquire and might release locks. This is an illustration of those restrictions. As the name two-phase locking suggests, we must have 2 phases when it comes to locking. In the first phase, the transaction can only acquire locks on objects but not release any. In the second phase, a transaction can release locks on objects, but it cannot acquire any. So if you look at the number of locks held by a transaction over its execution time, as illustrated in this plot here, on the x-axis, you have the execution time starting with the transaction start at the left and ending with the end of execution of one specific transaction. And on the y-axis, you have the number of locks that a transaction holds at the same time. And as you see here, during the first phase, the number of locks held can only increase, while in the second phase, the number of locks held can only decrease. So those are the two phases of two-phase locking. You have a summary of what I have just said. We have the phase in which we can acquire locks, and we have the phase in which we can only release locks. And that becomes very important, as we will see later, when we try to prove that this protocol guarantees that generated schedules are conflict serializable. And for that proof, we need that two-phase property. There's a couple of different variants of two-phase locking. First of all, we have conservative two-phase locking, which means that we do not allow transactions to acquire locks late. We require them to get all their locks at the beginning of execution. Also, there is strict two-phase locking, which means that we do not allow transactions to release locks early. They have to keep them until the end of execution. You can also combine those two, and then you get conservative strict two-phase locking, and the plain two-phase locking makes no restrictions whatsoever. So we can illustrate those different variants using the same graph as we have seen before, where we see how the number of locks of a transaction evolves over time. And as you see here, for the conservative two-phase locking variants, at the very beginning of execution, we always have a spike in the number of locks held. This is because we require conservative two-phase locking requires transactions to obtain all of their locks at once at the beginning of transaction execution. On the other side, you have the strict variants, and here you have the sudden drop at the end of the transaction. So this is because strict two-phase locking requires transactions to hold on to their locks until the end of execution, and they release all of those locks at once. Now, if you look at the non-conservative, non-strict two-phase locking, that's the plot that we have seen previously. Here we can have some kind of ramp up in the first phase and then some decrease in the second phase. Of course, this figure here is simplifying. If you would draw that plot for an actual transaction execution, you would get something much more messy, but the general tendencies that you see here, they do apply. So all of those variants of two-phase locking are used, and depending on the scenario, it depends on the scenario which one of them performs best. There's a couple of pros and cons about those different variants that I'm summarizing here. So generally, if you are non-conservative and non-strict, you are more permissive, which can be good for performance because it allows more transactions to interleave their steps and to essentially execute in parallel. The nice thing about conservative two-phase locking is that we prevent deadlocks, which can be bad for performance because you might have to abort transactions and restart them. On the other side, if we go for strict two-phase locking, then we avoid cascading abort. So especially in scenarios where it is quite likely that transactions abort. In those scenarios, it can be helpful to have something which essentially localizes the abort and avoids the chains of transactions that all have to abort because some initial transaction that they have directly or indirectly read from had to be aborted. So in general, you cannot say that one of them is better than the other one. It always depends on the specific workload, which of them works best. All right. So now we have seen two-phase locking. We need to convince ourselves that using it is really a good idea. Ultimately, what we want are conflict serializable schedules. We have justified why we want conflict serializable schedules in the last lecture. Now we have seen a concurrency control protocol, which seems to make sense. But at this point, how can we be sure that two-phase locking indeed leads to conflict serializable schedules? How can we exclude that users see any of the anomalies that we have discussed in previous lectures? In the following, we're gonna analyze two-phase locking formally, and we will prove the two-phase locking can only generate conflict serializable schedules. Is there any questions on two-phase locking before I proceed with that proof? If so, please ask them now in the chat. Otherwise, we will proceed. Okay. All right, one question is about a reminder of what conflict serializable was again. So conflict serializable essentially means that for a given schedule, we find another schedule that is serial, meaning it executes one transaction after the other one. And we find that our current schedule is conflict equivalent to the serial schedule. And two schedules are conflict equivalent if you can get from one schedule to the other one by only swapping operations that do not conflict. And two operations conflict if they execute on the same object, if they belong to different transactions, and if one of those two operations, at least one, is a write operation. And the point of plain two-phase locking, we could say yes, so conservative two-phase locking has this advantage that it avoids deadlocks, and strict two-phase locking has the advantage that it avoids cascading abort. So what is the point of plain two-phase locking without any of those extensions? The thing is that plain two-phase locking allows transactions to acquire locks late and to release them early, meaning that the total time that a transaction holds a lock decreases in average. And if a transaction holds a lock on an object, it prevents other transactions from accessing the same object. So the longer a transaction holds locks, the longer it makes other transactions wait. And that is bad for performance. So if you reduce the time that a transaction is holding a lock, you reduce the lock waiting time for other transactions. That means that you reduce idle time and your transactions in the system can process faster. So if deadlocks and cascading aborts are unlikely to happen, then you probably get the best performance with plain two-phase locking. And yeah, it's a justified question. I mean, it sounds scary. Deadlocks, cascading aborts. So one might think, why would people allow that to happen? But it really depends on the probability that it happens. If a deadlock is so unlikely that you would only have one deadlock per day and you process millions of transactions, then probably you would still do it. But same for cascading aborts. If transactions essentially never abort, then cascading aborts are also extremely unlikely. So probably if you have only one cascading abort per day or per year, then you probably want to reap the performance benefits offered by reducing lock waiting times. So in the end, it's a trade-off. You cannot say a priori which variant is best. It depends a lot on the properties of the workloads. And this is why different variants are implemented in practice. And yeah, so in the end, if you're really serious about performance tuning, then you might even try for a specific workload which of those variants works best. But a priori, you cannot say which one of them is the best. And plain 2PL, why is it better than a transaction that simply grabs a lock before it needs an object and releases it directly afterward? That's a great question. What is suggested here basically is something which doesn't necessarily follow the two phases of acquiring locks and releasing locks. So one could think, yes, why not? A transaction needs access to object A, so it acquires a lock on A, does what it needs to do with A, and then releases the lock on A. And then it needs to do something with object B. So it acquires the lock on B, operates on B, and releases the lock on B, and so on. In that way, I'm reducing the time during which locks are held. However, I'm not following those two phases of a two-phase locking, because the transaction would first release the lock on A and then again acquire a lock on B. And at this point, it is probably not clear why that is a problem. But during the proof that we are about to do, we will actually see why we need those two phases in order to guarantee that two-phase locking generates conflict-serializable schedules. So this is a great question. Let's table it for the moment, but it will become clear during the proof. Okay, great questions. All right, I think let's proceed with the proof. Okay. So this is an overview of the proof that we will do in the following. So we will essentially analyze schedules that were generated using a two-phase locking concurrency control protocol. And now we assume essentially, could it be that one of those generated schedules has a cycle in the conflict graph? Because if it has a cycle in the conflict graph, it means that it is not conflict serializable, as we have seen before. Now, in the following, we will essentially prove that if a schedule was generated using two-phase locking, it cannot have a cycle in the conflict graph, and therefore it must be conflict serializable. In order to conduct this proof, as a lemma, we will prove the following. We will prove this, what I call the release first lemma, which essentially says that if in the conflict graph I have a path from transaction 1 to transaction 2, then I must have that transaction 1 releases a lock on some object before transaction 2 acquires a lock on some object. So very important, we don't even require that transaction 1 and 2 are releasing and acquiring locks on the same object. It could be different objects. But if there's a path from one transaction to the other one in the conflict graph, then the first one must release a lock on some object before the second one acquires some lock. This lemma will be proven via induction. And induction generally means that you first prove something about a trivial case, and then you make the induction step, where you essentially reduce larger instances to smaller instances. Now, in this specific case, what we will do is we will first of all prove that this lemma holds for paths of length 1. So basically, we have just one step from one transaction to another one in the conflict graph. And in the induction step, we will prove that if the lemma holds for paths up to length I, then it will also hold for paths of length I plus 1. So we always extend the coverage of the lemma in terms of path length. This is the induction start. So we have two transactions, 1 and 2, and they have an edge connecting them in the conflict graph of the schedule. That means they have a conflict. And a conflict generally means that both of them work on the same object, and at least one of them is writing to the object. So we essentially have three possibilities. Either transaction 1 is reading object A and then transaction 2 is overriding it, or transaction 1 is writing to object A and then transaction 2 is reading it, or both of the transactions are writing to object A. So the second transaction is essentially overriding the value of the first transaction for A. Now, in all of those cases, what I need to have is that transaction 1 releases the object on A before transaction 2 acquires the lock on A. Now, transactions generally need locks in order to operate on objects. And here, for instance, for possibility 1, it seems that transaction 1 had at least the read lock on object A, so it can read the value. Transaction 2 needs a write lock, an exclusive lock, in order to write something to object A. Now, an exclusive lock and the read lock, they are mutually exclusive. So in order to grant an exclusive lock on object A to transaction 2, the lock manager first needs to get back the read lock for object A from transaction number 1. So here, definitely, in order to make this possible, in order to enable possibility 1, the lock, some lock on object A needs to get released and by transaction 1, and a lock on object A needs to be acquired by transaction 2. Now, the principle is similar for possibility 2, also for possibility 3. So here, basically, transaction 1 needs first to hold an exclusive lock on object A, and it needs to release that exclusive lock so that transaction 2 can acquire another exclusive lock on object A. So here again, we have what we want to prove in all of those cases. Because there's a conflict between them, we must have that transaction 1 releases a lock on some object before transaction 2 acquires a lock on some object. So this is what we want to prove. We have proven it for pairs of length 1. Now let's say that we have proven things for pairs length of up to I. And now we want to prove that this implies that it also holds for pairs that are one step longer. So here we want to extend for pairs with I nodes to pairs with I plus 1 nodes. All right. So first of all, we assume that we have already proven via induction that if I have a path of length of with up to I nodes, that the first transaction in that path releases a lock on some object before the last transaction on that path acquires a lock on some object. It doesn't have to be the same object. So we have proven this. We assume that we have proven this via induction. Now, looking at the connection between transaction I and I plus 1, using the same reasoning as on the previous slide, we also know that since there is a conflict between them, transaction I must release a lock on some object Z before transaction I plus 1 acquires a lock on Z. So this is even more specific than on the other side of the screen, because as long as we only consider one step and there's a conflict, we know that the conflict must concern the same object. So the locks get released and acquired for the same object. All right, so now those things. So I'm already close to proving the lemma. I want to prove that transaction 1 releases a lock on some object before transaction I plus 1 acquires a lock on some object. The question is just this. If I compare the lock acquirage, like the operation by which transaction I acquires a lock, and the operation by which transaction I releases a lock, which one of them happens first? We have had the question about why we need those two phases of a two-phase locking, and this is exactly the point at which we need them. Due to the properties, to the constraints of two-phase locking, I know that I have those two phases where first I only acquire locks and then I only release locks. And that means when considering this transaction I, if I have I acquires lock on Y and I releases lock on Z. Due to the constraints of two-phase locking, I know which of them must happen first, because transactions always acquire locks first before they release locks later. And that means, due to the properties of two-phase locking, I know that we must acquire the lock on Y before we release the lock on Z. Now I have here a happens before chain of events, and taken together, that means again that transaction 1 on that path releases a lock on X, before transaction I plus 1 on that path acquires a lock on Z. And this concludes the induction step. So by applying this recursively, I can essentially expand the lemma to paths of infinite length. And therefore, I know that if I have a path in a conflict graph from one transaction to the other one, the first transaction must release a lock before the last transaction acquires a lock. Now, how does this help me with the proof? Now, if I have this lemma, and I assume that I have a cycle in the conflict graph, then due to this lemma, it essentially says that some transaction in that cycle releases a lock before that same transaction acquires a lock, right? So we have a path from T1 to T2, means according to lemma, T1 releases lock before T2 acquires lock. Now I have a path from a transaction to itself, a cycle basically. That means that T1 releases a lock before T1 acquires a lock. And now again, we use the properties of two-phase locking, because that is not possible. Transaction cannot acquire a lock after it has released the first lock on any object. And because of that, I can conclude that I cannot have any cycles in a conflict graph as long as I use two-phase locking in order to generate them. Had I not used the constraints of two-phase locking, then there could very well be a cycle in the conflict graph that I'm generating, and that means that I don't get a conflict-serializable schedule. But since I made those restrictions of two-phase locking, because of that, I can be sure that all the schedules that I'm generating are conflict-serializable. All right, so now we have shown that using two-phase locking, we generate only conflict-serializable schedules. Now, the last interesting question, perhaps, when comparing two-phase locking to conflict-serializability here, is what about the other way around? Could two-phase locking, at least in principle, generate all schedules that are conflict-serializable? And as we see here, using an example, that is not the case. In fact, I wanted to ask you whether that can be the case based on the example that you see here. All right, I already gave you that. Okay, and it is also said on the slide. So we could not, in general, generate all the conflict-serializable schedules using two-phase locking. If you consider, for instance, this example here, this example schedule, transaction 1 writes something to object A, transaction 2 reads from object A and commits, transaction 3 reads object B and commits, transaction 1 writes again to object B and then commits. So if you would draw the conflict graph, we have 3 nodes, and we have 2 edges, and we have no cycle here. We have only this conflict on object A between transaction 1 and transaction 2, and then we have the conflict on B from transaction 3 to transaction 1. So this is conflict serializable. But the question is, could this have been generated using two-phase locking? If you have a second to think about it and put a proposition into the chat. If you think about where locks are requested and granted, could we have had this? if you think about which locks transaction 1, for instance, is acquiring and releasing. Okay, some first propositions here. Okay, very good. Yes, very good. Okay, so very good. Okay, so I have the correct solution by multiple people. Very good. Okay. All right, let's discuss it quickly in more detail. All right. So if you think about the lock requests, when transactions acquire locks and release locks, and we focus on transaction 1. All right. So the very first operation in the schedule is a write operation by transaction 1 on object A. And that means that transaction 1 clearly must have the write lock for object A, otherwise it couldn't write to it. Now, immediately after that, transaction 2 seems to be reading from object A. That means transaction 1 must have given up the write lock on A, because otherwise the read would not be permitted by a different transaction. So clearly, between the first step in the schedule and the second step, transaction 1 must have given up the lock on A. Now things continue. Here we have the commit, okay, and now transaction 3 is reading object B. So clearly at this point, transaction 3 must have a read lock on object B, and then it commits. And now transaction 1 writes to object B. That means that at this point, transaction 1 would need to have a write lock on object B. Now the question is, could it have had that lock maybe since transaction start? The answer is no, since just before that, transaction 3 has read from object B, so obviously transaction 3 had a read lock on B at that point. So transaction 1 must have acquired the lock on B directly before the write operation. But on the other side, it has released the lock on A after the first step in order to make it accessible to transaction 2. So what we would have here is that the first transaction first releases a lock before the lock on A, before it acquires another lock, which is the lock on B. And since two-phase locking does not allow transactions to acquire locks after they have released any, it means that this schedule here, despite being conflict serializable, it could not have been generated by two-phase locking. And that essentially answers the question. Now we have the full overview picture here. So we've discussed about all those different classes of schedules. We have all schedules contained within them are the final state serializable schedules, then the view serializable schedules, then the conflict serializable schedules. And now we know that two-phase locking essentially is a subset, like the schedules that could have been generated using two-phase locking, they are a subset of the conflict serializable schedules. And a small subset of that again would be the actually serial schedules. So this is basically what we can hope for. We guarantee that two-phase locking generates conflict serializable schedules, so we have no strange anomalies. Ideally, we of course would like two-phase locking to be able to consider all conflict serializable schedules. That is not the case, but nevertheless, two-phase locking is one of the most popular locking protocols used in practice. In the next lecture, we're going to discuss about a couple of extensions before we also discuss about different concurrency control methods. Wish you a nice weekend, and then I see you again next week.